giving me this opportunity to say in this conference, and welcome everyone to this workshop. So this workshop was organized on the request of Professor Gauri Shankar and I. We are talking about what that we on the other route, Professor.
It's not audible.
It's not audible?
No.
Now is it audible?
Yeah,
Hello?
yeah. Now it's better.
Now it's better? Okay. Okay. So now I'm audible, right?
Yeah.
Okay. So by Professor Gauri, yeah. So Professor Gauri Shankar and I are discussing about a joint initiative between the two departments of mathematics in the region, Mohali and Central University of Punjab. And this program is one such initiative that we envisaged together. So now the aim of the program is to expose young people to very basic differential geometry and some latest developments around that to encourage them study it further. So that's the aim, and that's how we have set up this program. I hope that it will be useful to some people. It is online, so there are certain things that one can do in in-person meeting is not possible here. But still, something is better than nothing. So with that note, I would request everyone to attend this program with and see how much they can learn from it. Thank you very much.
Thank you, sir. Our guest of honor for today's inaugural session is Professor Satya, NASI Senior Scientist and General Secretary, NASI Allahabad. He is the former Vice Chancellor of Rani Durgavati University, Jabalpur and APS University, Rewa. And his Secretary, IMS Professor Satya. I request Professor Satya to share his views with the participants. Over to you, sir.
Sir, it is not audible. It is not audible, sir.
Unmute,
Yeah,
sir.
just a second. Yeah. That's right. Now I think I'm audible, right?
Yes.
Okay. So I was saying that Vice Chancellor Professor Tiwari of Central Punjab University and Chief Guest of today's function, Professor R.S. Kulkarni, and all the resource persons who are going to give talks in this summer school, all the participants, all the invited guests. I'm very happy to be here in this inaugural function on behalf of the National Academy of Sciences, NASI. This is the second such program, NASI-TMC program, supported by the National Academy of Sciences, and I'm glad to see the presence of many young resource persons who will be giving a course of lectures on a topic of differential geometry. The enthusiasm of the participants drawn from all the parts of the country is quite visible. And I congratulate the organizers, Professor Gauri Shankar and Professor Krishnendu, and I hope that this will be a very successful summer school and will be unforgettable. Now, coming to the subject of differential geometry, I must say that this subject is really a very rich subject, amalgamating important branches of mathematics like the real analysis, advanced calculus, topology, Lie groups, and many other areas of mathematics. Professor Kulkarni, the chief guest of today's function, is one of the leading differential geometers of modern times, who has made some very remarkable original contributions in this subject in the beginning of his career. There are several eminent differential geometers in our country, but very few really understand the concept of modern differential geometry. The work of V.K. Patodi on Ather-Singer index theorem is the most cited Indian contribution in differential geometry. I hope many of you know that if you take a compact electric differential operator, then there are two types of indices associated with that operator. One is called the topological index, and the other is called the analytic index. And the Ather-Singer index theorem simply says that the two indices are same. And the contribution of Patodi was through giving a very different proof, very limited proof of this theorem using heat equations. Professor Kulkarni's understanding of topology and group theory puts him in a different class. Here in this summer school, you are concerned with the fundamentals of the subject, and I am sure the exposition of various resource persons will definitely make your learning process very interesting and enjoying. The topic, for example, the curves and surfaces, is a classical topic. In the differential geometry, but the differential geometry starts from there. A smooth manifold is another important topic which will take you to the modern differential geometry. Advanced calculus is the backbone of differential geometry, and students very often think that they really know the important theorems of advanced calculus, like the inverse function theorem and the implicit function theorem and so on. But sometimes I find that the confidence of dealing with these theorems is frequently missing. For example, let us take the inverse function theorem. What does it say? If we take a function f from an open set of Rn to the same open set of Rn, and suppose this function is such that its Jacobian at a particular point a1, a2, an is not equal to 0, then the theorem says that there exists a neighborhood V of fa1, fa2, fan such that f has an inverse defined on V, and f inverse is as smooth as the function f itself. In other words, roughly speaking, the inverse function theorem says that under these conditions, f has a local inverse. But if you want to really appreciate the theorem, you must see some examples. It's very important. In order to appreciate any big theorem, any important theorem, you have to see the examples which actually use that theorem or where the theorem is applied. And also you should see some particular cases. For example, if you want to appreciate the inverse function theorem, then try to see it's a special case only in one variable. And not only the statement, it will be very good if you try to prove it in the single variable case. Then you will really learn how important the theorem is in several variable case in its general form. I must say here a statement by Michael Ather, and he used to say that don't believe in a hi-fi theorem unless you see some special cases of that theorem. And that is really a very important thing. Now, coming to the classical topics that resource persons are going to deal with in this course, for example, the curves and surfaces. These are, of course, very basic objects, and everybody understands what a curve is. Now, for a layman, we say that a curve is really the path of a continuously moving particle in R3 or in R4 or in any higher dimensional Euclidean space. So, geometrically, you understand what a curve is, but a precise definition is very important. So, for example, in topology, a curve is simply a continuous map from the closed unit interval into the space. And if you see, sometimes people identify the curve as the image of the curve, but the continuous map itself is really the important thing which one must realize. Image is for us to see, to visualize how a curve looks like. But when we say that a continuous image of unit interval in a space is a curve, sometimes you will find that the image really does not look like a curve. I think many of you may be knowing that there is a continuous mapping from the unit interval into the square I cross I, which completely, it is onto mapping. In other words, there is a curve which fills up the whole square. I really will never like to call that the whole square is a curve because it is against your intuition. So it is very important, but topologists stick to that definition and it goes very well. But when you come to define a curve in differential geometry, you have to take a differentiable curve because only then you can really build up the concepts of geometry. For example, you can compute the arc length, you can think of the tangent, normal, and all those things associated with the curve. So there, your assumption has to be different. And it is only a continuous map. So sometimes we say that the domain space is a parameter space. And we sometimes we consider its equation. The equation of a curve is sometimes in Cartesian form, sometimes in polar form, but very often it is in parametric form, which is most important. So the parameterization of a curve is a very important concept. And when we come to differential geometry, we use a very special parameter, namely the arc length. And when you use the arc length as a parameter of a curve, really most of the concepts that you describe to study the properties of curve, they become very simple, very illuminating. Now, some of the important theorems of advanced calculus, as you know, everybody knows them, and we often quote them, like, for example, the Green's theorem, the Gauss's divergence theorem, the Stokes theorem. But the most important theorem that you will learn in this school is the Gauss-Bonnet theorem. Gauss-Bonnet theorem. And what is this theorem? So just roughly speaking, I want to tell you that this is a very important theorem connecting geometry with topology. And actually any theorem which connects two subjects in an intricate manner is the most beautiful thing to enjoy. If you take a compact two-dimensional Riemannian manifold, then there is something called Gauss curvature associated with that manifold. And also there is something called geodesic curvature associated with that thing. And the Gauss-Bonnet theorem says that the surface integral of the Gauss curvature of M plus the line integral of the geodesic curvature Kg of the boundary of the manifold M, that equals twice pi the Euler characteristic of the manifold. And as most of you know, the Euler characteristic is completely a topological concept. And the left-hand side, namely the surface integral of the Gauss curvature and the line integral of the geodesic curvature, these are all completely 100% differential geometry concept. And the two things, they are connected, that they are equal. That actually brings the beauty of this theorem called Gauss-Bonnet theorem. I refer to that Ather theorem and many important theorems of the subject. They are really special cases of Ather theorem, Riemann theorem. Even this Gauss-Bonnet theorem is a very special case of that. So what I want to say is that, particularly to the participants, that if you want to enjoy any subject, whether that is differential geometry or any area, it may be topology, it may be group theory, it may be Lie groups, it may be analysis, function analysis. If you want to really enjoy the subject, then try to understand the fundamental results yourself and see their special cases. And once the special cases are clear to you, then your own desire, you yourself will become very interested in learning the subject well, and then you can appreciate the high-phi theorem also, and then you really enjoy. And I am very sure that the resource persons whom I have noticed, most of them are from HRI, and they have been trained under Professor Kulkarni. They are going to explain you the subject, and that subject will be classical as well as the modern. And if you want to enjoy really differential geometry, your knowledge of topology has to be very good. Only then you will really be able to enjoy what is known as the global differential geometry. So with these few words, I congratulate the organizers of this workshop, Professor Gauri Shankar and Professor Krishnendu, and I'm sure that it is going to be a very successful conference. It will be really very beneficial, particularly to the research scholars and to the students, and you can start having a feeling for the subject. With these few words, I thank the organizers for inviting me to share my thoughts on this inaugural function. Thank you very much.
Thank you, sir. We are grateful for the time and efforts you took to share your thoughts with us. Thank you, sir. Now, chief guest of this inaugural session is Professor Ravi S. Kulkarni, who is the distinguished Professor Bhaskacharya Pratishtana Kunde, former professor at Johns Hopkins University, Columbia University, Indiana University, and City University of New York, USA, and IIT Bombay, former distinguished professor and director HRI Allahabad. Now, I request Professor Kulkarni to share his views with us. Over to you, sir.
Yeah, can you hear me?
Yes.
Yes,
sir.
Yes, sir. Vice Chancellor Professor R.P. Tiwari, Dean Visirika, Professor Gauri Shankar, Professor Krishnendu Gangopadhyay, all the resource persons of this workshop, and my friends. Professor Satyadev has given you a good background for the actual contents of this workshop, but let me just explain to you the initial title of the of this workshop. This is the NASI-TMC Summer School on Differential Geometry, organized by Professor Gauri Shankar and Krishnendu Gangopadhyay. I know they have worked very hard to make this school see the light of the day. But let me briefly say about NASI and TMC. NASI is a short form for National Academy of Sciences in India. It was the first national academy established by the great mathematical physicist Professor Meghnad Saha in 1930, who was a professor of physics at Allahabad University. Some of you may know his treatise on treatise on heat. It is actually contains a lot of mathematics. You may also know that Professor Meghnad Saha was a classmate of Professor S.N. Bose. You must have heard of Bose-Einstein statistics and so on. They were both students at the Presidency College and had a degree in mathematics. They contributed to physics, but they were mathematicians at heart. You see, mathematics is not exactly a laboratory science, but its structure is very much the same. You first collect the data and formulate the theories. And mathematics is really a theory builder for all sciences, for all rational thought. Now, Emil Saha's one of the really big achievement was establishing this National Academy, which brought the community of all scientists in India together. Now, let me say something about the TMC, or really I like TIMC, the Indian Mathematics Consortium. It is an umbrella organization of the mathematical societies in India. It is established in 2015. Its constituent math societies include Ramanujan Math Society, Calcutta Math Society, Gwalior Academy of Mathematical Sciences, and many others. And its institutional members also include some ICERs, universities, and IITs. Moreover, the very conception of mathematics that is adopted in TIMC is very broad. It certainly includes pure and applied mathematics, also mathematical theory building part in physics, chemistry, biology, medicine, statistics, engineering, and also some social sciences like economics. So this program is a joint program of these two organizations, NASI and TIMC. And Professor Satyadev mentioned this was the second program, I think he mentioned, but this is actually the third program of NASI and TIMC. Yeah, now let me give you a possibly very happy news. NASI and TIMC have agreed to strengthen the relationship further, and details are yet to be worked out, but we have agreed to establish a NASI-TIMC senior scientist position. And the senior scientist is supposed to initiate and conduct 5-6 such programs every year in the future. Now let me say a few things about the actual workshop. Differential geometry is actually on the borderline of pure mathematics and applied mathematics. This program itself, as you see, has two parts. The first part is curves and surfaces in Euclidean free space. Now this part is actually very useful in engineering, and when I gave courses at various times on this part, a good audience was from engineers. The second part is its natural extension, more theory in higher dimensions, and as Professor Satyadev mentioned, the very, very important concept of manifolds. This concept should be explained at the very beginning of our mathematical careers. Actually, in the undergraduate courses, I would like to say, and certainly in the at the master's level and PhD level. It's not merely a definition, but it's a certain point of view which was developed very clearly in Riemann's paper on hypotheses which underlie geometry. I'm very, very fond of this paper, and there are some English translations available of this, and you please see that. This theory, this paper was built on Gauss's work on curves and surfaces, and the important theorem in that paper was Theorem egregium, a local theorem. Professor Satyadev mentioned the Gauss-Bonnet theorem. That's a local global theorem, bringing together differential geometry and topology. But this Gaussian curvature is a really basic local idea that was introduced in Gauss's paper I think some 20, 30 years before. This Riemann's paper, who understood the whole structure, starting with manifolds, starting with higher dimensional manifolds, how they are necessary even in the investigation of lower dimensional manifolds, and developing a differential calculus on these manifolds. This is what differential geometry is about. And using the differential calculus is its strength as well as weakness, because there are certain natural phenomena which are not covered under differentiability hypothesis, and they come up in major theoretic aspects and many other aspects. So I think the higher parts in that second part are like Riemannian geometry, Lorentzian geometry, conformal geometry. These parts I hope will be covered by some of the experts whom we are invited for special talks. So I invite you all to enrich your understanding of mathematics through this workshop and through such programs, and enjoy.
Thank you, sir, for your enlightening talk. Now I request Dean in charge academics, Professor Ramakrishna Musrika, to address the participants. Over to you.
So good morning to all the participants for this on this wonderful day where the Department of Mathematics and Statistics is organizing the NASI-TMC summer school on differential geometry. So first of all, I would like to thank our guest of honor, Professor Satya Dio, and the chief guest, Professor Ravi Kulkarni, for taking the time to address this gathering. The blessings of our Honorable Vice Chancellor, Professor Tiwari, is always there to organize these kind of programs. So our Department of Mathematics and Statistics has worked very hard to organize this program, and it is very encouraging to know that more than 680 applicants have applied. So that shows how popular this program is. So we could only accommodate, as Dr. Gauri Shankar said, around 210. But it is a great step taken by them to keep this program on YouTube, so that a larger gathering, about more than these 210, those who could not enroll here or those who might be interested all over the world, they can get the benefit of this program, because this is something they are doing more like for societal benefit, right? Outreach program. So this is a really great initiative, and I would really appreciate all our faculty members and also the co-convener, Dr. Gangopadhyaya from ISER Mohali. So this is another great step that they are collaborating, going outside to other institutes, and they have got a stellar speaker list here, whom you will listen for the next few days. So with this, I won't take too much time so that the program can go on. And one more time, I would like to welcome all of you to this wonderful program and the summer school on differential geometry. And we hope that these kind of programs continue in the future, not only in mathematics, but other places. And the National Academy of Sciences and Mathematics Consortium, we are grateful to these two organizations that they have come forward and helped us financially, and also from a scientific perspective, they have come out and helped us. And we would like to continue this kind of collaboration and conduct more summer schools in other areas of science, and not only in our school, but different schools in the university. So this will benefit everybody in the university and outside. I think this is a great initiative these organizations are doing for the benefit of all of us. Thank you very much.
Thank you, sir. Now I request our Honorable Vice Chancellor, Professor R.P. Tiwari, to give his referential remarks. Over to you, sir.
Yeah. Professor Ravi S. Kulkarni, the chief guest of this 3 weeks NASI-TMC sponsored summer school on differential geometry. Guest of honor, Professor Satya Dio, Professor Gangopadhyaya, Professor Musurika, Professor Gauri Shankar, all faculty members and research scholars of Central University of Punjab, esteemed resource persons from across the country, and also dear participants from different parts of the country. Good morning to you all, and Sat Sri Akal from the land of 10 gurus, and also from the land which is drained by 5 sacred rivers. Professor Kulkarni and Professor Satya, both of them have already set the tone for discussion, deliberations, and learning that will happen in the coming 3 weeks on this very important topic, which has very historical significance for our country as well. You know, the only use of differential geometry that I have known as a non-mathematician is its extensive use in Harappan civilization, and the imprints of that huge, wonderful huge, is available in the archaeological diggings that have happened in that civilization. And of course, it has varied applications which have, as Professor Mukherjee said, that differential geometry is in fact at the borderline of pure and applied mathematics, and certainly it has a wide range of applications. Even in space science, where positioning of satellites are largely determined or done on the basis of differential geometric calculations. Also in the study of black holes, and in n number of applications. In fact, I was going through with the course module that Professor Gauri Shankar has given to me, and here I find some interesting things like geodesic curvature, where this is extensively used in geophysics, particularly for studying the motion of plate motions, their directions, and also the rate of motion of the plates. So this is extensively used there. And also another that attracted me is Euler's theorem, where we study the polar wandering and how much actually the wandering has happened and how polar reversals take place. So these are the things that I can really talk about in today's program. As all of you know, I'm not from this area, therefore I'm not venturing to talk much on this. But what I would like to make certain points for consideration of NASI-TMC, because we have the Secretary of NASI here. Nowadays, the focus of any workshop, any summer school, and for that matter, even on the classroom teaching and pursuing some program is on learning outcomes. These are the wonderful exercises. Here, a lot of time, money, efforts, energy goes within the organized programs like this. So our endeavor should be to give best out of such programs, and that can happen only when we define learning outcomes of any exercise of this nature, and then accordingly plan as to how these outcomes are really transferred to the participants, to the beneficiary. So, of course, the course module is given, but I would like to draw, inspiration from Mukherjee by saying that if some of the direct applications of these modules where the participants can really do some hands-on experiments and really feel the significance of this wonderful branch of science, and because, Professor Mukherjee also at the end said that enjoy. So, in my opinion, the real enjoyment of this exercise can come when participants can really do some hands-on exercise and direct application of this very, source of knowledge. So that's one. And this NEP 2020 also emphasizes on this that the experiential learning, which has been one of the main drawbacks of learning system of India, where a lot of theoretization, emphasis is given on theoretization, and classroom teaching is also a sort of passing out of information on particular topic. So, to make it more attractive, to make it more enjoyable, and to really derive maximum benefit from exercises like this, sort of experiential learning. And another buzzword now in the learning system is blended learning, where we have mix of theoretical and practical exercises on any topic to really make the learners, the participants, not only attentive, but also to make them really understand the subject, the concept, and to actually be able to apply those concepts for solving various problems of the society, of the nation, and also of the science. So that is there, And another point that I would like to make really, whether, once we define the learning outcomes, and then and we need to test whether the participants have really obtained those learning outcomes. And that and there is very simple geometrical calculation on this. And it's like this: when the program begins, what is the domain knowledge, what is the knowledge level of the participants? If that is tested before the workshop like this commences. And then at the end, so this will really give us how such exercises have been really beneficial and whether the time, money, energy, and efforts that we make, whether corresponding to that, the benefit has really, the beneficiaries have really achieved and gained those learning outcomes. So with these two suggestions, I'd like to thank NASI-TMC, Professor Kulkarni, Professor Satyadev, for considering our university to one of the hosts for this wonderful program. And also I compliment Professor Gauri Shankar and all his friends from the department for proposing it to NASI and convincing them that that Central University of Punjab would be the best host and best venue for conducting this workshop. And of course, Professor Satyadev has been the Vice Chancellor of APS University Riva, from where I graduated in 1977. Sir, I am from Riva, I am from Sirmaur. The
very
road
great.
that university is located, that is Sirmaur Road, APS University Riva. I left
I'm very glad to hear.
1977, then I went to Sagar, and from there I went to Northeast. So Northeast, I was there for 32 years. In 2015, I came back to Sagar as Vice Chancellor, and by God's grace and the grace of 10 Gurus, now I have got this opportunity to serve this Central University of Punjab. So my special compliments to you, sir. And I really hope and most sincerely wish that Professor Gauri Shankar has made all arrangements, that the strength that I derive from the type of resource persons that are lined up for this workshop. It's really wonderful, and it is, all of them are really the experts in their field. So the participants will really gain. Now the biggest objection to online learning and online workshop webinars like this is that the type of interaction that happens in face-to-face gatherings doesn't really happen. So if the resource person can really make it much more interactive, so that it doesn't remain simply a monologue, but the participants really participate in the discussion, they take part, they understand, and they solve their queries, they get opportunity to whatever they want to know or whatever they are not understood, to just deliberations, so that this really becomes meaningful. So with these few words, I'd like to again compliment NASI-TMC, Professor Kulkarni and Professor Satyadev for spending out their time for this workshop. Thank you. Jai Hind, Jai Bharat.
Thank you, sir. Your words are always a source of inspiration for us. Thank you. Now I invite my colleague Dr. Sachin Kumar to present the board of friends. Over to you, sir.
Thank you, ma'am. Am I audible?
Yes, sir.
Okay. Worthy Vice Chancellor Professor R.P. Tiwari ji, today's guest of honor, Honorable Professor Satyadev ji, and today's chief guest, distinguished Professor Ravi S. Kulkarni ji, respected Dean in Charge Academics, Professor R. Vasurika ji, respected Dean Students Welfare, Professor V.K. Garg ji, our respected Dean Research, Deans of Schools, HODs, and all fraternity of Central University of Punjab, distinguished guests, participants, and dear students. Good evening, good morning, everyone. I consider it a great privilege to propose a vote of thanks to all the distinct dignitaries who have made it convenient to attend the inaugural session of NASI-TMC Summer School on Differential Geometry. First of all, my sincere thanks to the Almighty God for making today's event a grand success. We are deeply grateful to the today's guest of honor, respected Professor Satyadev ji, for presiding over this function and for an enlightening address. His address was unique because of novelty of ideas as well as style. Sir, I thank you for presiding over this function and for your address. I take this opportunity to express our sincere thanks to respected Professor Ravi S. Kulkarni ji for gracing this occasion as the chief guest. His presence today in this function has immensely enhanced its importance. We are extremely grateful to you, sir, for your insightful address. I would also like to thank our Honorable Vice Chancellor, Professor Raghwinder Singh P. Tiwari ji, for sparing the time for joining the event and for your enlightening presidential address, and for your encouragement for conducting this event. We are extremely grateful to you, sir. I would also like to thank Professor Ramakrishna, Dean in charge academics, for the Dean address and for your guidance and motivation. Now, I am thankful to Professor Krishnendu Gogopadhyay, co-convener of this summer school, for giving us the opportunity to hold this summer school. Thank you, sir, for your continuous support and advice, which have greatly helped towards the organization of this summer school. I want to thank Professor Gorishankar, sir, head of the Department of Mathematics and Statistics and convener of this summer school, for the initiative he took in holding this event, and also for deciding to invite guest of honor, respected Professor Satya Deoji, and for inviting the eminent Professor Ravi S. Kulkarni ji as today's chief guest. For guidance to us in all the activities and ensure that we always do the right things in a right way. I am very much thankful to the sponsors of this summer school, NASI and TMC. Without their generous financial support, it would not have been possible to organize this summer school. I also express my sincere thanks to other esteemed guests who have taken keen interest in the program and have taken a time out of their busy schedule to attend this event. Also, thank you to all the participants of the summer school and everyone who joined this event for paying your attention. Lastly, my thanks are due to my colleagues and research scholars in the Department of Mathematics and Statistics and the supporting staff who have worked with great dedication to make this event a great success. Thank you all, sir. Over to you, ma'am.
Thank you, sir. Now I request you all to please rise for this national anthem. Thanks everyone. Participants are requested to remain connected to the online session. We'll be starting for 6th chord lecture of the day within a few minutes.
10 minutes.
10 minutes, within 10 minutes.
Thank you, Dr. Saab. I am very happy to know that you were at Riva.
यस सर प्लीज सिरमौर के पास एक छोटा सा गांव है, मैं वहां से हूँ।
हाँ, नहीं मैं गया हूँ, और गया हूँ, कई बार गया हूँ।
जी जी
बड़ी अच्छी बात है
जी डॉक्टर साहब जी।
चलिए आज
जी
इतने दिन के बाद किसी ऐसी व्यक्ति से मुलाकात हुई जो रीवा से कनेक्शन है इनका।
जी जी डॉक्टर साहब, और आपको पधारना है थोड़ा कि कोरोना की स्थिति और ठीक हो तो फिर आप पधारे यहाँ।
हाँ हाँ बिल्कुल बिल्कुल, अब आप करिए, अब तो यू आर नाउ
जरूर
वेरी रिस्पॉन्सिबल पोजीशन।
जी
तो अच्छे अच्छे प्रोग्राम करते जाइए, बढ़िया रहेगा।
जरूर डॉक्टर साहब, थैंक यू।
लेट द यूनिवर्सिटी कम इन लाइमलाइट।
श्योर डॉक्टर साहब, थैंक यू।
I think I should thank Professor Satyadev for bringing out this NASI-TMC senior scientist position. I think his help is very much appreciated, and I hope it becomes a reality. Some details are to be worked out yet.
Yes, it will become, and I am really happy that I could be of some help. Thank you, Dr. Sir.
ठीक है सर, नमस्कार सर।
नमस्ते नमस्ते।
Is Professor Dani here? Professor Dani here? Professor Dani, Professor Kapil Paranjpe, Venkateshwar Tiwari.
Hello.
Venkateshwar. Oh,
Yes, sir.
hello, Venkateshwar.
Yes, sir. Yeah.
Kapil. Kapil.
Yeah. Hello.
And Dani?
No, he is not here.
Oh, he's not here.
Yeah.
Okay.
Harish Seshadri?
The
Seshadri?
program.
No,
Maybe-
Harish Shadri is also not.
Okay, Professor Kulkarni, nice to see you.
Guru Raja is here. Guru Raja is here.
Oh, yeah, okay.
Yeah.
Let me see his face at least.
Professor Paranjpe is there. I mean, he just said hi to me.
Guru Raja, where is Guru Raja?
Eh,
Today EL today EL 2 day EL ಅಂತಿದೆ.
Once again, I welcome you all to this event and I extend my warm welcome to our today's speaker, Dr. Abhishek Mukherjee, Department of Mathematics, Kalna College, the University of Burdwan. And first of all, I request Dr. Sachin Kumar to please introduce the speaker. Over to you, sir.
Thank you, ma'am. First of all, thank you, Dr. Mukherjee, for accepting our invitation for delivering the lecture in this summer school. Dr. Abhishek Mukherjee is an assistant professor in Department of Mathematics, Kalna College, the University of Burdwan. Broader area of his research interest is topology, geometry, complex analysis, hyperbolic geometry, and hyperbolic spaces. He has organized and attended many international and national conferences and workshops. He is a gold medalist in pure mathematics. He has a good international publication to his credit. He has more than 11 years of teaching experience. In short, I have given a brief introduction, but it has list is long. Now I invite Dr. Abhishek Mukherjee to deliver the first talk of the summer school. Over to you, sir.
Thank you. Good morning, everyone. And I would like to express my deepest gratitude towards the organizers for making me a part of this summer school, and I would like to pay my regards to Kulkarni sir, Satyadev sir, and Dr. Gangavadai, and I would like to wish all the best to the participants and organizers for this summer school. Yeah. So, may I start the session or?
Yes, sir. Yes, sir. You must start
Yes.
the session.
Okay. Okay. Thank you. Can you see my screen?
Yes, sir. It's visible.
Okay. Okay. Okay.
Yes, sir.
As my part, okay. Okay. Thank you. Thank you. As my part of the course is very basic and it needs a quick visit on differential calculus on several variables. So I would like to just give a brief discussion on calculus, functions of several variables, to go forward to the next discussion on differential geometry of curves. Okay. So first of all, I would like to consider, suppose given a function given a map f. So let us recall the definition that we have already did in real analysis. So suppose you have a map f from the open interval AB to R, and let us consider a point in the open interval AB. Then the definition was like that. So the derivative has been defined. So derivative of f at x naught has been defined as a real number, which is the limit minus this by h, if it exists. Okay. If this limit exists, then you can define this as a derivative of f at that point. And we denote it by, as you all know, f dash x naught. Okay. Now, coming to this definition once again, if you just look at this difference, then the Taylor's theorem could be represented as like this, and a term containing h. Okay, where this will be called it is the remainder which will be satisfying limit h tends to 0. This is going to be 0. Okay. So one can define that the difference, the derivative of f at x naught can be defined in this way, that if the difference fx naught plus h minus fx naught, it can be approximated by this term. Okay. But what is that? This is actually a map from R to R defined by this. Okay. And this map is not a common one. It has some special property, that is it is a linear map. Yeah. Okay. So our definition of differentiation of f at x naught can be rewritten in this way, that we can rewrite the definition as, so f is said to be differentiable at x naught if there exists a linear map lambda from R to R satisfying limit of h tends to 0 mod of f x naught plus h minus f x naught minus lambda of h by norm h is going to be 0. And this lambda is called this the derivative of the map f at x naught. And generally you can denote this one by f dashed x naught, or one can denote by df at x naught. Okay, fine. Okay, now we can extend this definition that has been taken up for these real numbers. We can extend the definition to higher dimensions, and for this one you need to consider so suppose you take an open set. Suppose we are dealing with Rn, Euclidean space having standard norm. So V is a subset of Rn which is considered to be an open set, and on this open set you are defining a map to another Euclidean space Rk. Okay, and suppose you take a point inside B, then this map F is said to be differentiable at x naught if there exists a linear map lambda from Rn to Rk. Okay, so if there exists a linear map, as you have seen in a particular situation in R, so if there exists a linear map lambda from Rn to Rk satisfying that limit h tends to 0, norm of this fx naught plus h minus fx naught minus lambda of h by norm h is going to be 0. Okay, now I would like to leave it as an exercise that check whether the lambda is unique or not. Okay. So left as an exercise. Okay. Okay. So you can prove that this lambda is unique. So I would like to left this as an exercise, and we'd like to denote this by as above. So denote it by f dash x naught, or if you like, you can denote this by a df x naught. Okay. Okay. And f is said to be differentiable over v if it is differentiable at every point of the open set v. Okay. 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 Now let us move towards the definition of partial derivatives. Okay. So suppose you consider a map or an open set V subset of Rn to Rk. Okay. And with respect to standard basis considered of Rn, and for Rk, that is, suppose you take the standard basis here, which could be denoted by E1 E2 N, and suppose you take this as E1 E2 UK. Okay. Then effects can be represented as a linear combination of I equals to 1 to k fi x ui. Okay. But these functions, these fi's, these are actually maps from V to R. So these are called component functions. Component functions of f. Okay. That is a phi is actually the pi compose f. Right? Pi is the ith projection map. Okay. Now you can define the partial derivative in this way. That is just you consider the limit, that is limit t tends to 0 if I this is actually x naught, right? Okay, x naught plus t ej minus fi x naught by t. So if it exists, then this limit will be called the partial derivative of f with respect to xj. Okay, so you can so this is the partial derivative. Sorry. Xj. And you can denote it by dj fi at x naught. Okay. Or something you can denote usually by del fi del xj. Okay. And you can prove that if f from this to k be differentiable at x naught, then your partial derivatives will exist. So del fi del xj's exist, and you can represent the derivative of f at x naught, and if you take the jth component, then it will be summation this del fi del xj at x naught ui. Okay, right. And with the help of this theorem, actually this gives us, so this is actually this is the jth column vector of the matrix associated with the linear map, that is the derivative of f at x naught. We can denote it by this one. So this is actually the jth column vector of the matrix associated with this linear map f dash x naught. Okay, and so this partial derivative del fi del xj will occupy the ijth position of that matrix. Okay, so that is, so this implies the matrix will be having the entries. So this is actually, so del f1 del x1 at x naught, del f1 del xn at x naught, and you can write down all the rows, and the last one is del fk del x1 at x naught, del fk del xn at x naught. Okay, and this is called the Jacobian matrix of the differentiable map f at x naught. Okay. Okay. Now, if you consider the map from an open set V of Rn to Rn, then this will be a square matrix of order n cross n, and then you can associate. So if f will be a map from Rn to Rn, the differentiable at x naught belongs to V, then one can talk of the Jacobian determinant, then one can talk of the Jacobian determinant. Okay, of f at x naught, and we can denote it by, suppose, j f at x naught. Okay, so this will be the determinant of this matrix. Okay. Fine. Okay. Yeah. Yeah. So now, with the help of the partial derivatives, one can show that f is differentiable at x naught if all its partial derivatives exist and continuous. Okay. So, okay. Let us move. Okay. Yeah. Okay. So I can define this as, okay. So f is said to be a C1 map if with the help of the partial derivative, I'm defining this. Okay, so it's said to be a C1 map if the partial derivatives exist and continuous over V, and this is true for all I, 1 less equal to I less equal to k, and for all j where 1 less equal to j less equal to m. Okay, and just take this. So I have to give it as an assignment that define a CK map. Okay. Yeah. Could be taken up for your tutorial sessions. Okay. On your own. So you can extend the definition of this definition. Yeah. Okay. Fine. Now let us recall the very important kind of very important theorem, which is the inverse function theorem, and then okay. So let us. So this is the inverse function theorem. Okay. So I'd like to. Before that, I would like to write a note here that whenever you are defining, so if f, yeah, Rk be a differentiable map at x naught, then you are getting a linear map from Rn to Rk, right? Which is the derivative of f at x naught. So your f dash x naught is a linear map. It is in the vector space of all linear maps from Rn to I'm sorry, this is Rk, and this corresponds to a map from V to this f dash x naught. Yeah. Okay. Fine. So this is so corresponding to a differentiable map at x naught. You are associating a map from V to f dash x naught from V to the linear space of all linear transformations from Rn to Rk. Okay. And this space will be equipped with the norm, that is norm T is the soup of norm Tx in this one. Okay. Okay. Fine. So whenever we are defining that f is continuously differentiable, so that means f is differentiable and this map is continuous. Okay. 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 So now let us write down the statement of inverse function theorem. So let me check. Already, yeah. So the inverse function theorem. So suppose that f is a map from an open set Rn to Rn and BC1. Okay. And let us suppose that your image of f of V is T. Now, if the Jacobian determinant that is at the point, suppose x naught not equal to 0 for some x naught belongs to V, then there exist two open sets, suppose V dashed, which is in V, and another one containing x naught, and another one is W, which is in T, containing FA, Fx naught. Okay, and a uniquely determined map G from G from W V dashed such that number one, f is 1 1 on V dashed, and since G has been defined on W, so G is actually the inverse of f over B dashed. And number 3, G is also C1 over W, and you can compute the derivative of G, that is G dashed at Fx naught will be 1 by f dashed of x naught. Yeah. Okay. So locally, so if f is C1, then, and if your Jacobian determinant is non-zero, that is the matrix, if the matrix is non-singular, then locally you are getting a C1 map, which is the inverse of f. Okay, fine. Now let us move to the differential geometry of curves, and so the first question can be emerged out as, what do you mean by a curve? Okay. So intuitively speaking, a curve will be thought of as deformations of straight lines. Okay. And an one-dimensional object, and the maps we used to describe a curve do not have to be necessarily, in general, continuously differentiable. But to avoid some complications, in particular, we will take continuously differentiable curves through which we can define a very important notion, which is the arc length parameter, that has been mentioned by Satyadeva sir. And so firstly, we would like to define a parameterized curve, and before that, suppose we consider an interval I is an interval in R in the real line, but this interval it is usually open. Sometimes it may be closed, and maybe it is unbounded. That is, we can write, we denote this I as something like this, AB, where maybe A is plus infinity and B is minus infinity. Okay. Okay. So generally we are denoting this interval as like this, and we are defining parameterized curve in R3. We shall deal the cases for R3 that can be generalized to higher dimensions.
Sir, I think A is minus infinity, B is plus infinity.
Oh, I'm sorry. Yeah. Sorry. So let us define that a CK parameterized curve in R3 is nothing but a CK map. Is a in R3 is actually a CK map. Suppose we denote the curve by alpha. So it is actually a CK map from AB to R3. Okay. So that means corresponding to each point in the interval, that is T, you are corresponding to a point whose components can be denoted by xt, yt, zt. It is the alpha t, right? So this is a point in R3. And these x, y, z are component functions of alpha over I. So alpha is CK, means the real valued maps, the component functions x, y, z are CK. Okay. And notably, these are in particular continuous. Okay. So alpha is CK if and only if the real valued maps x, y, z RCK. Okay. In our discussion, we shall assume that the order of differentiability k is high enough so that we do not need to mention it every time, and we will use the general term in this regard. It is a smooth parameterized curve, which means that it is at least C1, and in any situation, if k order derivatives involved, at least Ck. Okay, so generally we termed it as, we would like to we call this as smooth parameterized curve. Okay. And in this regard, so if you consider the image of this curve, so the image alpha of I, which is a subset of R3, so this is called the trace of alpha. Okay. Trace of alpha. Sometimes it is called the graph of okay, is a trace of alpha. Okay, and if for a point t0, if alpha t0 equals to x0, then we say that the parameterized curve passes through the point x0. Okay. Okay. And if alpha be a smooth parameterized curve in R3, then its first derivative is its first derivative, that is, which can be written as alpha dash t. So this is actually the vector which is x dash t, y dash t, and z dash t, and it is a vector in R3, and it is defined to be the tangent vector or one may say that is a velocity vector of the curve alpha at t. Okay. Okay. That means if this is your alpha and this is your t, then if it moves like this, so this is your the direction of the tangent vector. Okay. So let us have a look at some examples. The first one is very simple one, that is.
Excuse me.
Yes, sir. Yes.
Yes. Confusion here. The tangent vector at t or at t, it is tangent to the curve in R3. So it is in the tangent space of t alpha t R3.
Yes, yes. Can you repeat, please? I'm just.
Yes. In my opinion, the tangent vector, can you please slide your diagram? Yes. So this tangent vector is at alpha t. At alpha t. So it belongs to tangent space t alpha t R3.
Yes, sir. Okay.
I think it is more accurate version if it is at alpha t rather than at t.
Okay. Yeah. Okay.
Excuse me, sir. But anyway, that is isomorphic to R3. So it is not wrong if we write it R3 as well.
Sir, in most of the books, they don't put arrow above alpha. So I think it is proper to put arrow above alpha. If it is not convenient, then we can ignore it.
Yeah. Now we can use this. So you'd like to put an arrow over alpha. This is some books have used it, but we are not using here. Yeah.
Yes, sir. It may not be convenient every time in writing.
Yeah. Yes. Okay. Okay. So the first example is a very simplest one. That is, suppose you take an arbitrary point. Suppose an arbitrary point x naught, and you can choose a fixed non-zero point a naught, a fixed non-zero point. Yeah. Okay. Then one can think of a map which is from R to R3, and you can define it as, so alpha t, so is x naught plus t a naught, and this will be called a straight line in R3, and the passing through x naught in the direction of a naught. Okay. One may also think of a map, suppose alpha star, so by just defining it, x naught plus, suppose you take, okay, so this one, yeah. So the common criteria, the common feature of
alpha star t.
Right.
Yes.
Yeah. The common feature of these two maps is that their traces are same. Okay. Now, if you would like to compute the first derivative, then for the first one, so your alpha dash t, so this will be actually a naught, and this is true for all t belongs to R. But for the second case, alpha star dash t, so this will be 3 t square a naught, right? Yeah. Okay. So if you look at this map, so this is so at 0, then alpha dash 0 is a0, a naught, and alpha star dash 0 is 0. Okay. So we'll come to this particular situation later. This type of curves will be named with a particular name. Okay. 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 One may consider another example here. Suppose let us choose another alpha and okay, suppose beta from an interval I from minus epsilon to 2 pi plus epsilon to suppose to R2 be defined as here. Suppose alpha t equals to sin t and your beta t is cos of 2t sine of for all t belongs to I. Okay. Then here also you can see that their traces are same, and so if we denote the trace of any curve by this notation, so this will be these are same, and this is actually the unit circle. Okay. Yes.
Excuse me. I think in this case, alpha is not 1-to-1.
No. Yes. Yes.
And please say something about regularity as well, because we are taking every time tangent vector.
Yeah, I'm coming to this point. Yeah, I'm coming to this regularity of curves.
Okay.
Yeah. Okay. So now, if you want to compute the first derivative, then it will be suppose so it is actually so alpha dash t will be half of.
My point is that because this curve is being some sort of I mean it is an immersion, so injectivity is needed or not?
Yes.
For this alpha, do we need injectivity or not in the definition of a curve? So it should be injective immersion or just immersion?
No. Self intersection has been allowed here. Yeah. Or at this stage. Yeah.
See.
Yeah.
I see. So are you okay? Local impedance is no issue.
Yeah. Okay. 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 So let us put some remarks. So I'm coming to other examples later. So let us have a look at some remarks.
Some echo is going on. Hello.
Hello.
I request all the participants to please mute yourself.
Okay. So the first one is that suppose your parameterized curve alpha has a property that it satisfies that alpha dash at t naught is non-zero for some belongs to I, then one can define the tangent line. So you can define the tangent line through alpha at alpha t naught passing through the point alpha t naught and parallel to the tangent vector. Okay, so passing through alpha t naught and parallel to alpha dash t naught. Yeah. Okay, so if this happens, then you can define the tangent line to the curve at the point alpha t naught. Okay. So from the if you look at the example 1, then you have seen that the tangent vector of the first curve was constant. Okay, that is, so I would like to put it remark 2. That is, in the first example, you have seen that the tangent vector is constant, and the image of the curve, so that will be a part of a straight line. Okay, that is, if your tangent vector is a constant, suppose is a constant vector a naught, so a naught, a constant vector, then we can say that by integrating, so it will be of the form, so it is some ta naught plus b naught, right? So b naught is another vector. Yeah. Okay. Now if your a naught is non-zero, that is, if you suppose that a naught is non-zero, then we can go for the parametric equation of the straight line parallel to a naught passing through the point b naught in this way. That is, it is actually xt can be regarded as t, and your yt is ta naught plus b naught. It's true for all t belongs to R. Okay. But on the other hand, if your a naught is 0, then the image will be a single point, that is namely b naught. Okay. So whose equation can be thought of as y equal to b naught. Okay. Now, third remark is that, now let us look at this example. Suppose be defined by alpha t equal to, suppose, t cube minus 4t t square minus 4 is true for all t belongs to R. Okay. And here it should be noted that this alpha is not 1 1, right? Because if you take, so note that is alpha 2, yeah, right? So at this stage, the smooth parametric curve alpha is not required to be 1 1. Okay. So alpha is not required to be 1 1 in general. Okay. That is, self intersection have been allowed here. Okay. So this is you can draw the trace of this curve. It is actually, so this is, the drawing is very bad, but okay. Yeah. So here you see that a self intersection is there. Okay. Okay. The next one is that suppose you now consider another example, that is so for all t belongs to I, then as you all know that this is the trace is the graph of the function. Yeah. So here you see that if you look at this alpha, then one can check that alpha is smooth. Now I would like to leave it as an exercise for the tutorial session, that what do you think of the differentiability of the function f at uh, at x equal to 0. Yeah. Yeah. And if you draw the graph of this map, this curve, this is actually this one. Okay. And from the picture, these are called the prototype of cusp, and this may be regarded as nodes. Okay. Okay. So now it's time to define the regular parameterized curve, which is going to be, the definition is like that alpha is said to be regular if alpha dash t not equal to 0. You can think of tangent lines at every point of the curve. Okay. And if a curve, for some t alpha dash t is 0, then the point alpha t is called a singular point. Okay. But we are concerned about the curves without having singular points. Okay. So we are dealing with these regular curves. Okay. Now, so let us have a look at some remarks. So if alpha be a regular curve, as I have already said, that you can define a straight line containing the point at the point alpha t parallel to the vector alpha dash t, right? And which is defined as the tangent line to alpha at t. So regularity allows us to talk of tangent lines at each point to the curve. Okay. So to study differential geometry of a curve, it is essential that there exist such tangent lines at every point. Okay. So it is essential that there exist tangent lines at every point. Okay, and this condition guarantees this this requirement. Okay. Secondly, Now, if you go back to the example 1, then you observe that the straight line has been represented through two curves. One is alpha and another one is alpha star. But alpha is regular, whereas alpha star was not. Okay? So this says that the same trace may correspond to a regular curve and a non-regular parameterized curve. Okay. So yeah. So this says that the absence of regularity at a point doesn't necessarily indicate the geometric equalities of the curve at that point. Okay? Because the traces were same, but one is regular, another one is non-regular. Okay. Okay. Now, if you look at another example of regular curves, suppose let us look at this example that defined by, so this is alpha t, that is suppose 3t by 1 plus t cube and 3t square by 1 plus t cube, and it has been defined over sorry, minus 1 to b. Yeah. Okay. So the curve will look like this one, that is just sorry, yeah, okay. And it should be noted that the trace is a graph of the equation this is, so the graph of the equation x cube plus y cube equal to 3xy. Okay? And it should be noted that if you look at the alpha t, so this is so you can just make it like this, 3 by okay, yeah, so this is t square 1 by this, and the second one is 3 by t, yeah, yes, and this says that this will be tending to 0 0 as t moves towards plus infinity. Okay. So an epsilon neighborhood around 0 will map to the set, which looks like something like this one. This part, and there is another one that is this one. Yeah. Okay. Okay. And it is an exercise that
I'm sorry. Hello.
excuse me. In this example, may I say something, sir?
Hello. Hello.
May I say something? I would like to ask some questions.
I think it will be better to ask these questions in tutorial sessions.
Okay.
Let him go. Please continue, Dr. Mukherjee. Dr. Abhishek, please continue.
Abhishek sir, I think you were muted. Please unmute.
It is
Okay. Can you hear me? Yeah. Okay.
Yes.
Okay. So you can check that this curve is not regular. At t equal to 0. So this says that the analytic singularity has put an impact on the curve and that reveals the geometric singularity of something like a cusp, right? So regularity condition rules out this kind of peculiarity, that is the cases of cusp, but it will not exclude the case of self-intersections. Okay. So to eliminate this one, we need to impose some other further conditions. Okay. Now recall that we have already seen that different parameterized curves may have the same trace. Okay. And notably, we are interested in the trace of the curve as a set of points in R3. So this requires to introduce some relations between the parameterized curves that ensures the same trace. Okay. And for reasons, it will become clear that why we are confining ourselves to regular curves, and certainly passing from parameterized representation of the trace to another one. This I can say that if you change the parameterization of the trace, the regularity condition will not be changed. Okay. So let us see the definition. What I would like to establish here, that is, suppose you take a curve from alpha from I to R3 and another one from another interval j to R3. Okay. So considering two parameterized curves, alpha and beta. So a diffeomorphism phi from I to j such that alpha equals to beta compose phi is defined to be a reparameterization or you can say that a change of parameter okay, yeah, okay, and two smooth parameterized curves suppose alpha and beta are said to be, suppose alpha beta are said to be equivalent if you can find out a reparameterization if there is a reparameterization phi. Yeah. Suppose alpha is from I to R3 and beta is from J to R3, then phi from I to J. Okay. And if two smooth parameterized curves are equivalent, then one is said to be a reparameterization of the another one. Okay. And note that, so this definition tells us that the relation of being reparameterization will be an equivalence relation. Okay. So being reparameterization is equivalence relation, okay, on the set of all smooth parameterized curves. Okay, so you can denote it by this one. Okay, another interesting feature of this definition is that suppose you take two curves, alpha and beta, and if they are equivalent, then this will imply that their traces are same. Okay. Okay. If you take two curves, alpha and alpha bar, which are equivalent, then you will see that their traces remain same. Okay. So they are enjoying the same geometric features. Okay. 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 Now let alpha let beta be a reparameterization of alpha. Okay. Then one can think of alpha as by definition it is beta compose phi, where phi is a change of parameter, where phi is a change of parameter. Okay. Then what would be the first derivative of alpha? What is alpha dash t? What is alpha dash t? This is, if you can apply chain rule, then this is actually beta dash of phi t, phi dash t, right? Okay. So this says that okay. So the effect of the reparameterization can be thought of as modification of the speed, that is the velocity with which the trajectory, that means the trace of the curve. So if a particle moves on the trajectory. So the reparametrization will be a modification of the velocity or speed of that particle, which whenever it is moving. Okay. Yeah. For instance, if you take, okay, so if your phi dash t is negative, less than 0, then you can say that the trajectory is traversed in the opposite sense, keeping the same direction. Okay? And note that the speed vectors or velocity vectors of two equivalent parameterized curves at the corresponding points will have the same direction but may enjoy different speeds and sense. Okay. Okay. Yeah. Now, if you go back to the to this one, and if you think of the converse of that remark, that is if you take the converse of the second remark, then what can you say? You can say that the converse will not be true in general, because if you look at the example 1, we'll see that alpha and alpha star both have the same trace without being equivalent. Okay. 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 Now, amongst all the smooth parameterized curves that are equivalent to a given smooth parameterized curve, we would like to find out a special smooth parameterized curve which will play an important role in this theory. Okay, and definitely it will simplify the many proofs in the theory of curves, although in most of the cases it will be very much complicated to find it analytically, which says that the finding out that parameter limits the practical value of this. Okay, so let us define what kind of parameter is required here. That is, so first define that a smooth, I'm just writing curve, a parameterized curve alpha from I to R3 is defined to be naturally parameterized if the norm of alpha dash t equals to 1. And it says that the curve will have unit speed. So the curves can be thought of as, so it is a unit speed curve. Okay. And we shall denote the parameter. So now particularly we shall denote this natural parameter from now on as small s. Okay. Okay. And it should be noted that whenever you are talking about a unit speed curve, so certainly it is regular. as it is evident from the definition here. Okay. So now our intention, our goal is to construct a parameterized curve which is naturally parameterized and equivalent to the given parameterized curve. Okay. So to make it possible, we need to introduce the notion of a very important part of this theory, which is arc length. Okay. Now one may ask a question that what would be a possible way to think of arc length of a parameterized curve from some point to another one. Okay. So what do we do? So suppose you take a curve. Okay. So you would like to define the arc length. Suppose this is your curve is alpha. This is your alpha A, and this is alpha B. Okay. So you are considering a closed interval inside this I. Okay. And our goal is to define the arc length of alpha from alpha A to alpha B in a very natural way. So what we do, we just subdivide this interval to a partition. Okay. So suppose you take a partition this one, and with respect to which you can put the points corresponding to the subdivisional points. That is, it is your alpha T1, alpha T2, and moves on. This is your alpha Tn minus 1, and you just connecting these points through straight lines. Okay. Yeah. Okay. And take the sum of these lengths. Okay, that is, form the sum alpha subject to the partition P. Okay, that is, it is the sum of all the lengths of these arcs. Yeah, is I equal to 1 to n. Yeah. Okay. So now we see that so we can prove a very interesting theorem that will give you the possible object to define the arc length. Okay. So what is that? Now for this partition we just define the norm of that, which will be the maximum of all the lengths of the subintervals. Okay, that is Ti k minus 1, where I runs over 1 to n. Okay. So one can prove that you can think of this theorem, and that for every epsilon greater than 0, one can find out a delta such that for every partition P having its norm less than delta, that is, for every partition P of over AB, I'm sorry, over AB with its norm less than delta, we have mod of the sum that has been defined above, that is subject to the partition P, minus minus integration over AB of the function norm of alpha dash t dt. So it will be less than epsilon. Okay. How much time I have?
Five minutes more, sir.
Okay. Okay. So this theorem says that this object is going to be a possible definition of arc length of the curve alpha from alpha A to alpha B, right? Okay. So I would like to give a sketch of the proof, and the scheme
Once again, it is
will
echoing.
be, yes. Okay.
And echo is going on.
So okay, yeah. Okay, so we can define, we just introduce a map F from this set. To R, okay. Defined by, that is F of T1, T2, T3 will be square root of x dashed T1 square y dashed T2 square plus z dashed T3 square. Okay, where these x, y, z are components of this curve, right? Okay, and your T1, T3 lives in the closed interval AB. Okay. Now, as you see that the set that we have considered is a compact set, and since the function that we have defined is continuous. Okay. So we should note that this is continuous, and since it has been defined over a compact set, so it will be uniformly continuous, right? Okay, and through this uniform continuity of F, so you will have, so for a given epsilon greater than 0, so for a given epsilon greater than 0, so due to the uniform continuity of this function, you can have a delta greater than 0, satisfying that mod of F T1, T2, T3 minus F of, suppose, okay, S1, S2, S3, and it will be less than, we'll just take this epsilon. Okay, whenever the modulus of T1 minus S1 will be less than delta, modulus of T2 minus S2 will be less than delta, modulus of T3 minus S3 will be less than delta. Now, how do you proceed? Now just go for these component functions, and then you can apply the mean value theorem to each of these component functions x, y, z, and you will get, so I'm writing this, so by using this one, so you will have so mod of your subdivisional points were, yeah, so consider the subinterval Ti minus 1 Ti, okay? So over the subinterval, this one. So I'm going to use this MBT of x, y, z over this subinterval. Then you will have, so xti minus 1, that can be written as mod of x dash some xi, the length of the subinterval, that is ti minus 1, where xi is sitting inside the subinterval. Okay. Similarly, you can go for the other functions, and you will get that yti minus 1, that will be y dash of some eta multiplied by the length of the subinterval, yeah, where eta is sitting inside ti minus 1 ti, and again for the third one, this is z dash of some delta I ti minus 1, where delta is sitting inside ti minus 1 ti. Okay, yeah. Now with the help of these three equations, you can compute the length of the curve through the connecting straight line segment from alpha ti minus 1 to alpha ti. Okay, so that is norm of alpha ti minus alpha ti minus 1. I'm sorry. Yeah. Okay. So you can check on your own that it will be something like that. That is f of xi, eta I, and the last one is delta I. Yes, delta I multiplied by the length. Okay, that means, so if you consider the sum, that is LAB alpha subject to the partition P, then it is the sum of s to 1 to n f of xi I, eta I, delta I, ti minus 1. Yeah. Okay. Okay, it's okay for now. Okay, so now if now move on to the integration, that is integration a to b of the map norm alpha dash t over a b. Okay, so this integration can be written as a sum of the integrals over each subintervals, that is summation of I equal to 1 to n integration ti minus 1 to ti mod alpha dash t, I'm sorry, dt. Okay. Now using MBT of these integrals, so in each of the subinterval you are getting a point. Okay. So this will be I equal to 1 to n. So this is norm of alpha dash zeta I ti minus 1 by using the MBT to the integral each of these integrals. and this Ti is in the open interval Ti minus 1 Ti. Okay, and this says that you can, if you can compute this one, it is actually summation f of Ti 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 minus 1. Okay, so for the partition P with its norm less than delta, you will definitely get that each of the length Ti minus 1, it is less than delta. And since your points xi, eta, delta I and the zeta is in the subinterval Ti minus 1 Ti, so their lengths, that is, if you look at the lengths of the points, this will be less than delta, this will be less than delta, and the last one is, this is also less than delta. Now I think the rest part can be deduced easily. Okay, okay, so the game is over for now. So length of this minus the norm of minus dt, I'm sorry, it will be less than epsilon. Okay.
Yes, sir.
Yeah.
Hello.
Yeah.
Dr. Abhishek, have you finished?
Yes, yes. Finished
Okay.
for today. Yeah.
Okay, thanks. All the participants are requested to go through the exercises given by Dr. Abhishek, and these will be discussed in tutorial session in the evening session, that is going to be between 4 to 5. So next we will meet for the next session after lunch, and that will be from 2 p.m. onwards. So please join well on time for that session. Thank you.
Will this note be made available?
We will try.
Okay, one thing, please give some reference book, and if it is possible to send us the PDF of the book.
Yes, that will be certainly provided.
Okay.
Okay.
Thank you.
Okay.